Hi everyone. So in this video, we're going to be learning about something called the unit circle. And we'll see later on this week that the unit circle is going to be a really important tool for us to evaluate different trigonometric functions. However, we're not there yet. We're not going to be talking about trigonometry at all in this video or the next video. But just know that, why are we learning this? We're learning it because it's going to really help us out with trigonometry, which is going to be like the main kind of topic of this class. So if you've taken a trigonometry class before, you might already have a picture in your head when I say the word unit circle or the words unit circle. You might be picturing this diagram with all these different angles and all these different points on it. I want you to kind of forget about that for now. We'll get there, but really when I say the unit circle, all that actually refers to is a circle of radius 1 centered at the point 0, 0. That's all the unit circle actually is. Let me write that down. So the unit circle is just a circle of radius 1, and it is centered at the origin, which is the point 0, 0. So I think a lot of people tend to once you learn about how, the connections between the unit circle and trigonometry, you start to kind of give all this extra complexity to the unit circle. But really at the end of the day, all the unit circle refers to is a circle like the one I have drawn right here. So it's a circle with radius 1, meaning that the distance from the center to any point on that circle is 1. And then the circle is centered at 0, 0, rather than centered somewhere else. So I want to just label a few points here to kind of give some context. So because we know that this circle has a radius of 1 and it's centered at 0, 0, we can mark down what these 4 points are, right? So the first point that I did on the positive x-axis, that would be the point 1, 0. Then we have the point 0, 1. Over here we have the point -1, 0. And down here we have the point 0, -1. And where am I getting those numbers from? I'm basically just using the fact that, again, the radius is 1, right? And so if we're measuring a distance of 1 in all these different directions, it will change whether we're changing the x coordinate to 1 or the y coordinate to 1 or the x coordinate to -1 or the y coordinate to -1. But all of those are just going the distance of 1 in those 4 directions. But also, if you were to go to some other random point on the unit circle, this distance would also be 1, right? Because it is the unit circle. So I want to come up with the equation for the unit circle. And in order to do that, I want to remind you about the equation of a circle in general. So remember that this is something you should have learned in your 141 class, your Pre-Calculus 1 class. So the equation of a circle with a center of the point HK. So we're using H to represent the x coordinate of the center and K to represent the y coordinate of the center. And then additionally a radius. We'll use the letter R to represent the radius. If you have a circle with that center and that radius, the equation of that circle is going to be x minus the x coordinate of the center, so x minus h squared, plus y minus, and then from there we subtract the y coordinate of the center, so y minus k squared is equal to, and then on the right-hand side we have r squared. And if you don't remember learning this, or you are like a little rusty on it and you want to kind of relearn where this comes from, I'm going to link my 141 video that goes over this. That video will show you exactly where this formula comes from. Basically, it comes from the distance formula. And again, coming back to this idea that when you have a circle, any point on the circle is the same distance, is the radius distance from the center. So with that in mind, we can now write down the equation of the unit circle, right? So using this formula, so the unit circle we know is centered at 0, 0, and it has a radius of 1. And so what this tells us is that the equation of the unit circle is, so we're just going to go and take this formula that I wrote above, and we're going to write, instead of h and k, we're going to put 0, 0, right? Because those are the points, the coordinates of our center. And then instead of r, we put 1. And so for the first part, we just have x minus 0 squared. That's the same thing as just x squared, right? And then for the second part, we have y minus 0 squared. Well, that's the same thing as y squared, y squared. And then on the right-hand side, we have 1 squared, and that's just 1. So basically, that the formula that I wrote above really simplifies to this very clean, simple formula for the unit circle. Okay, so I want to do a little bit of work with working with this equation and kind of making sure we understand what the relationship is between the equation of a graph and points on that graph. So actually, let me scroll back up for a second. So in general, if you have a graph, let's say you have a line or a parabola or a circle like we do here, and if you have the equation of that graph and you're trying to figure out whether a point lies on that graph, what do you generally do? Like, how do you test, given an equation, how do you use that point to test whether it lies on the graph or not? You plug it into the equation, right? So any point that lies on a graph must satisfy the equation of that graph. That's like the definition of the equation of a graph. And so in this case, if we want to test whether some certain points lie on the unit circle, we need to verify that they satisfy x squared plus y squared is equal to 1. So let's start with this first one. We already know that this actually does lie on the unit circle, right? Because we plotted that point right there. We can just kind of visually see that it lies there, but let's actually verify that it satisfies the equation. So basically all we need to do is take the x coordinate, which is -1 squared, plus the y coordinate, which is 0 squared, and we want to just check, does that actually give us 1 the way it's supposed to? And in this case, we get -1 squared becomes +1, and 1 plus 0 is in fact equal to 1. And so that tells us that, yes, this point does lie on the graph. And by the way, one thing I should just quickly mention, when we're talking about points lying on a circle, and in general, when we talk about a circle as like a graph, we're only referring to the outside of the circle. Like if you had a point that, for example, was like here, that is not considered to lie on the circle. The circle just refers to all the points out here, right? Because these are all the points that are an equal distance from the center. This point and this point and this point and this point, those are all different distances from the center. So when we're talking about a circle, we're just referring to the points around the outside of it. Okay, so let's check another one. So this is the point 3/5, -4/5. So this one is a little harder to tell whether it lies on the circle or not, right? Like it looks like maybe it could. So 3/5, -4/5. That would be something like, 3/5 is like a little more than a half, -4/5. Maybe it's like down here somewhere, but we don't know for sure. So let's actually check it out. So we just want to take these coordinates again and plug them into our equation and check, do we get an equality? Do we get something that is true? So 3/5 squared plus -4/5 squared. We want to verify, is that equal to 1? So in this case, we get 3 over 5 squared, right? You do 3 squared over 5 squared, so that's 9 over 25. And then here we have -4 squared is 16 over 5 squared is 25. And we're checking whether that is equal to 1. So here we can add together our numerators and we get 25 over 25, and that is in fact equal to 1, right? And so that tells us that, yes, this point does lie on the unit circle because it satisfies the equation. All right, let's do one more. So this one is the point -1/3, 2/3, which again, if you look at the picture, it seems like it could be reasonable. So like -1/3, 2/3, looks like maybe a little bit off, but it looks like it's at least plausible that, it's a point that lies somewhere around here. So let's see what happens when we try to plug this one in. So if we do -1/3 squared plus 2/3 squared is equal to 1. negative 1/3 squared, well, that is equal to 1 over 9. And then 2/3 squared, that's equal to 4 over 9. And so if we add these two fractions together, we get 5 over 9. And 5 over 9 is not the same as 1, right? And so that tells us that no, this point does not lie on the unit circle. So what we just did here, like I said, this applies for any graph. You can always test out whether points lie in a graph by plugging into the equation. But this idea of kind of working with the equation of the unit circle, we'll actually see will become really important when we get to trigonometry as well. So I think in the last video of the week, we're going to be coming back to the same equation and working with it in a similar way. So I want to do one more related example, but there's one other thing I need to introduce first. So you probably have learned this in a previous class. I'm not sure when you first learned this in most math classes, but there are, if you look at the XY coordinate plane, there are 4 different zones, right? There's this part and this part and this part and this part. And so those different zones are sometimes referred to as the 4 quadrants. So let me write that down. The 4 quadrants. So the way that we label these 4 quadrants is we start in the quadrant where both X and Y are positive, right? So that's over here. If you have a point that's over here, the X and the Y coordinate are both going to be positive, right? And so this quadrant we refer to as quadrant 1, and we usually write them with Roman numerals. So that's quadrant 1, and then you go counterclockwise. So this would be quadrant 2, and this would be quadrant 3, and this would be quadrant 4. And so I'm just bringing this up now because it will kind of come up in the next problem, and then also it will definitely come up all throughout the course. So I just want to make sure everyone knows what I'm talking about when I'm referring to the 4 quadrants. Okay, so let's do another question, kind of like the last few we did. So this time, instead of testing whether a particular point lies on the unit circle, we're told that a point lies on the unit circle, but we're not told what the y coordinate is. And so we need to figure out what could the y coordinate be in order to make this point lie on the unit circle. So basically, if this point does, let me say it this way, if the point 2, 5, y lies on the unit circle, and by the way, I forgot to mention this throughout this video, but as always, feel free to pause the video and try these examples yourself. Especially after we did the other ones, maybe you can try this one yourself. So yeah, if this point lies on the unit circle, it must satisfy x squared plus y squared is equal to 1. Right? And so what we can do is we can take this point and plug it into that equation and use that information to solve for what y must be. So if we take 2/5 and then we just have y squared because we don't know what y is yet, and we know it's equal to 1, now we can solve for y. So 2 over 5 squared, that's going to be 4 over 25 plus y squared is equal to 1. Now we want to make a common denominator, right? Because we want to subtract this over. Maybe let me write out one more step. So how would we, isolate y? Well, we want to start by subtracting 4 over 25. So we're going to have 1 minus 4 over 25. And then we want to make a common denominator to actually do this subtraction. So 1 is 25 over 25. Y squared is equal to that. Important difference. And so if we do this subtraction, we find that y squared is equal to 21 over 25. But we're not done yet, right? Because we're not trying to find y squared, we're trying to find just y. And so now we need to take the square root of both sides. But importantly, when you take the square root of both sides, you have to include a plus or minus, right? Because we don't know whether y is positive or negative. So if you have a number and you square it, it always gives you something positive. But that, when you square it, you kind of lose track of whether the original number was positive or negative. Just to give a complete side examples, this will probably seem unrelated, but for example, let's say you know that x squared is equal to 9. Well, there would be 2 different possibilities for what x could be, right? X could be equal to 3, but x could also be equal to -3. because both positive and negative 3, when you square them, the negative sign goes away and it becomes positive 9. And so it's the exact same idea up here. We need to, when we take the square root of both sides, we have to write y is equal to plus or minus square root of 21 over 25. And then we can simplify these a little bit. So y is equal to plus or minus still. Whenever you're taking the square root of a fraction, you can take the square root of the numerator and the denominator separately, which sometimes allows you to simplify parts of the fraction. So in this case, square root of 21, that doesn't simplify. There's actually really no way to break that down any further. 21 is equal to 7 times 3, and neither of those is a perfect square, so we can't even factor out a perfect square. But on the other hand, the denominator, well, the square root of 25, that's just 5. And so this is our answer. Y could either be positive square root of 21 over 5, or y could be negative square root of 21 over 5. And I want to just kind of show you a picture to think about this, why this is the case. So what's going back to the original information that was given to us, we were told that the point 2/5 comma y lies on the unit circle. So let's try to estimate where that point would lie. So remember that this point here is the point 1, 0. So 2/5 would be a little less than halfway between the origin and that point, right? Like forgetting about the circle for a second, just thinking about, distances. If this is 0 and this is 1, 2/5 might be somewhere like here, maybe, probably a little further along, because 2.5 over 5, or 2 over 5 is a little bit less than 1/2 is what I'm trying to say here. So maybe like that. And so if we know that that is our x coordinate, well, there are two different points that have that same x coordinate, right? It could have been this one, but it also could have been this one. And so those are the two different points that we're talking about here. The first one is the point 2/5 positive square root of 21 over 5. And then the other one down here, this one is 2/5 and then negative square root of 21 over 5. So in this problem, I told you find all possible values for y, but oftentimes in this style of question, you'll be also told what quadrant the point lies in. So instead, if I had wanted you to find just one of these 2 points, I could have said, suppose the point 2/5 comma y lies on the unit circle in quadrant 1. So if you knew it lay in quadrant 1, then that would tell you is this point. If I instead told you that it had to be in quadrant 4, then you would know it's this point. In this case, I said find all possible values, so that's why we found both of them. But this is just something important that we're going to see all throughout talking about trigonometry, this idea that for one given x value, there's two different y values, right, when you're on the circle. And same thing, if we are given an x value, if we're given a y value, there will also be two different x values, just because of all of the symmetry that you have when you're working with a circle. Okay, so we're going to change gears a little bit for the remainder of this video, and we're going to talk about something that is called the terminal point of an angle. Let me write that on the top here. So the terminal point of an angle. Okay, so remember that we talked about when we first introduced angles, we talked about the terminal side, right? We talked about how you have your initial side. So if you're just graphing an angle kind of floating on its own, you have your initial side like this, and then you have your terminal side up here. And here's your angle. And then when we draw our angles on the unit circle, not on the unit circle, in standard position, we no longer need to draw that initial side, we just draw the terminal side, right? So we do something like that and say, okay, here's our angle. So the terminal point refers to the place that if you draw your angle in standard position, it refers to the place that the terminal side intersects the unit circle. So let me write that down. So if theta, remember theta is just the Greek letter that we will sometimes be using to refer to angles. So if theta is an angle, specifically an angle graphed in standard position, so graphed on the xy coordinate plane, like we said, so that the initial side is along the positive x-axis. So if you have your angle graphed in standard position, then its terminal point is the point where its terminal side intersects the unit circle. So to give you an example here, let me just redraw this a little bit neater, and actually I'll just draw a bigger angle. So let's say that we have an angle theta that looks like this. So let's say this is our angle theta. The terminal point of this angle would be this point here, the point where the terminal side intersects the unit circle. So let me just label that. So this point here would be referred to as the terminal point. Okay, so I want to do some practice finding the terminal points for some different angles. Again, trust me that this is going to be important. It might seem a little random right now, like why are we doing this? But when we get to trigonometry, we'll see that this is essential. So very important stuff for the remainder of the class. So I want to go and find the terminal points for each of the following angles. So this is one that I would recommend pausing the video and doing it yourself. Remember again that we're working with the unit circle. So basically we know what these 4 points are on the unit circle, right? Because we did that on the first page, and that is going to be important in answering these. So we're finding the terminal point where we'll start with just pi over 2 and pi. Okay, so starting with pi over 2, remember that pi over 2 is 90 degrees. So that's one of the ones that I think it's really important that you have kind of memorized. But you can always get to it by remembering that pi is 180, right? So pi over 2 is half of 180, half of 180 is 90. So pi over 2 would look like this as an angle. And so that would give you a terminal side that is just along the positive y-axis. And so the terminal point, again, is just this point where that terminal side intersects the unit circle. So in this case, that would be the point 0, 1. Right? Because we know that, that the radius is 1, so that has to be the point 0, 1. Okay, so next up we have an angle of pi. So, So next up we have an angle of pi. So as we just mentioned, pi is equal to 180 degrees, right? So this would be this angle here. And so our terminal side would just be this negative x-axis. And so the terminal point would be this point here. And again, just by using the fact that we know the radius of this circle is 1, that would be the point -1, 0. Okay, couple more. So next up we have 3 pi over 2. So again, I encourage you to pause and do these next couple yourself. So 3 pi over 2, well, that's just 3 multiples of pi over 2, right? So I encourage you to think about your angles this way. 3 pi over 2 is 3 times pi over 2. We know that pi over 2 is 90, and so 3 times 90 is going to be, so here's 1 times 90, 2 times 90, 3 times 90, right? So it's going to give you this angle down here. And so our terminal side would look like this, and then the terminal point is going to be this point right here. And so just using the fact that we know the radius is 1, we would know that this is the point 0, -1. Okay, next up we have, actually I lied, we have 2 more. And these 2 are a little bit different, right? Because these are going to be, these are now angles that are not quite just between 0 and 2 pi, so it might take a little bit more work to figure out what these angles are. So first of all, we have 5 pi over 2. So let's first just try to figure out, like, where does that angle lie on the unit circle? Well, 5 pi over 2 is more than 2 pi. So how do I know that? Well, 4 pi over 2 would be 2 pi, right? So 5 pi over 2 must be more than 2 pi. Or another way you could think about it is this is the same thing as 5/2 times pi. And 5/2 is 2.5. So that is more than 2. So we know it's above 2 pi. And so we just need to figure out how much more than 2 pi it is. And so really we can do that by just saying, okay, well, we know that 2 pi is 4 pi over 2. And so how much extra do we have? Well, we have another pi over 2. So this is going to be 2 pi plus pi over 2. And so where is that going to put us? Well, it's going to put us the same place that we were for pi over 2, right? So the angle is going to go all the way around like this. And it's going to put us right back where we were on the first example we did. So remember, we learned a word for this type of situation. 5 pi over 2 and pi over 2 are not the same angle, right? They are different. One of them is just this small rotation. Pi over 2 is just a 90-degree rotation. 5 pi over 2 goes all the way around in a circle and back. So it's not the same angle. However, it is what we call coterminal. So 5 pi over 2 and pi over 2 are coterminal angles. And so if we compare them, so there's pi over 2, the terminal point was 0, 1. And now for 5 pi over 2, the terminal point is also 0, 1. So again, I know that right now this probably seems maybe a little bit overly simple and sort of, why are we doing this? Just trust me, it's going to be important. And one of the most important things I want you to get out of this video is the fact that coterminal angles have the same terminal point. So I'll write that down in a moment after we do this next one, because we'll see this next one is another example of this phenomenon. And actually, let me just write down the fact that it's coterminal so that you have that in your notes. So for this first one, we said that this angle is coterminal with the angle pi over 2. Okay, so next up we have negative pi. So that angle is also going to be coterminal with one of the angles we already did. This one's going to be coterminal with pi, right? Because negative pi would be measuring 180 degrees, but going this way instead of this way. And so it's going to put us at the same part of the unit circle that we were at when we did pi, and we end up with the same terminal point. So the terminal point for this one is also -1, 0. So this one is coterminal with the angle pi. And then let me just write down that fact that I just told you, because like I said, this is going to be really important moving forward. Note that coterminal angles have the same terminal point. And that's just because they kind of show up at the same part of you know, they have the same terminal side, right? So if they have the same terminal side, they must have the same terminal point. All right, almost done with this video. There's one more thing I just want to quickly mention, just in case you're kind of following along in your book. If you look in your book, you'll see that in this section, when they talk about terminal points, they talk about them a little bit differently than the way we are. So I just want to kind of explain how the book describes them, and then also just try to convince you that it's really equivalent to the way that we're doing it. So note, your book, instead of referring to the terminal point of an angle, your book refers to the terminal point of an arc. And I'll explain what I mean by that in a second. Of an arc instead of an angle. So when I say arc, it's exactly the definition of arc that we learned in the video. I think it was actually our last video, right? When we talked about arcs and sectors. So for example, let's say that you go to a particular angle. So I'm going to draw a picture, kind of like our first picture when we were talking about terminal points. So let's say you're going to an angle of theta. Your book, instead of talking about the angle, they talk about this arc. I'm going to try to do that a little neater by just making this a thicker pen. That would probably be nice. Okay. So it turns out that the length of the arc that I just highlighted in purple is actually the same as this angle. And it comes back to that arc length formula that we learned in our last video. So let me kind of try to describe this in words, and then I'll show you kind of mathematically what's going on. But these definitions are actually equivalent. Because when you're in the unit circle, so the unit circle has a radius of 1, and so if we apply the arc length formula, we'll see that the length of the arc is actually the same as the angle. So because in a circle of radius 1, the arc length is equal to the central angle. So to remind you, the arc length formula that we learned the other day was that arc length is equal to the radius of the circle you're looking at multiplied with the central angle of that arc. And in this case, if we're working with the unit circle, the radius is just 1, right? So you just get 1 times theta, which is just theta. And so basically, just to go back to an example, for example, here, let's say pi over 2. Instead of referring to this as an angle of pi over 2, I could have said it was an arc of pi over 2. And that would really mean the same thing, because the length of the arc that you would get from here to here is the same, has a measurement of pi over 2, which is the same as that central angle. So I don't want you to worry about that too much. I just want you to know that if you look in the book, you'll see that the language is a little bit different, but everything works out to be the same. And it really, like I said, comes down to this, this arc length formula that we learned the other day. All right, that is it for this video. As I mentioned, in the next video, we're going to do a whole bunch more with finding terminal points of angles on the unit circle. And yeah, I'll see you all in that next video.